How to perform Opensees using nonlinear static procedures and pushovers analysis in Etabs software. What does Opensees stand for? It stands for the Open System for Earthquake Engineering Simulation. Opensees is a software framework for developing an application to simulate the behavior of structural and geotechnical systems subjected to static and dynamic loading. Etabs offer nonlinear static procedures, also called NSP, for seismic evaluation of existing and new building. NSP has two principal components, that is, pushover analysis and site response spectrum. Nonlinear timing history analysis offer a great accuracy. That is, nonlinear time history analysis offer greater accuracy and less uncertainty when compared to static procedures, that is NSPs. But NSP can still provide a reasonable idea of global behavior and possible failure modes of a building with substantially less computation efforts. NSP converts multiple degree of freedom modes utilizing pushover analysis to determine capacity curves, and typically in the form of base shear versus displacement at the roof. And the use of ground spectrum. The use of ground spectrum in some form with this capacity curve can estimate the maximum global displacement. There are two different types of NSPs. That is, the capacity spectrum method and the displacement coefficient method. CSM, or capacity spectrum method, is based on an equivalent linearization approach such as used in the FEMA 440 equivalent linearization, or FEMA 440 EL. Here, pushover curve is converted to a spectral acceleration and spectral curve. On the other hand, DCM, or displacement coefficient method, converts spectral acceleration into elastic displacement such as used in the ASCE 4113. Here, pushover curve is used to determine effective stiffness and period, and when used with response spectrum gives spectral acceleration. I'm going to show you how to perform pushover analysis in Etabs. That is the Opensees analysis. I'm going to open this one. So we can start by defining or Defining load cases to run. So define load patterns, load cases, we start by running dead and live load. Define load patterns. So analyze load cases to run. Do not run, 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 run. We run live and dead load cases only for this model. And you can see the model the way it behaves for linear static analysis. So let's now run nonlinear static analysis. I will unlock the model. We will start by assigning hinges in our beams and columns. So I'll go to select. I'll select by object type. I'll select beams, select. Then assign frame hinges. So you can modify, or let's just delete all of these, then reassign again. So add according to table ASCE 4113, we're going to assign table for concrete beam. We're going to assign for moment 3, load case is dead, then okay. That is at the beginning of column, at the start point and at the end. So the relative distance is 1 at the end. Now the same properties for concrete beam, okay. Now you can see we have assigned hinges at the start and the end of those beams. I'm going to select object type, columns, select, close. Then I'm going to assign frame hinges. Again, add. Now this time change to concrete columns. You can change to PM13 or just M3. So I prefer this. Then okay. Again add. Now this time at the end. So relative distance is 1 at the end of each column, and then the same. Okay. Now we're going to select everything and then assign frame, assign hinge overrides. Make sure auto subdivide frame object is checked. Then okay. Now you can see how it has divided the hinge at the start and the end of each column and beams. We're now going to assign to define pushover load case. So we're going to go to define load case, then add new non-linear static. Now we're going to start by defining a dead plus 25% live load case. This will help the program to use this as a starting point for pushover load case. So I'm going to add dead load and add. Now this time live load 25%, that is 0.25 of live load, and then okay. Now I can just modify and just name this as dead load plus 25% live load. Okay. Now add new case, push. The name is pushover, is nonlinear static. We're going to continue from state at the end of nonlinear case. I'm going to select dead load plus 25 live load. And then model lead case or load application modify. We're going to use displacement control. And you can alter the displacement you want, maybe say 500, add story 4, and then okay, that is 500 millimeter. And then results saved modify. We're going to use multiple states. And then okay, so that we can be able to access the results during the analysis, and then click OK. So we're going to continue. There's no point of doing that. Then click OK. So going to define load cases for pushover. Let's modify, add. Now this time is acceleration. Make sure it's acceleration in the UX, and the scale factor is -1. That is the error. Then click OK. So make sure it's acceleration UX -1. Then click OK. Then define load cases, modify. So this one we've already modified displacement and everything. Okay. We want to use grid point E story 4. Grid point E story 4 as our control point. So I'm going to run analysis. I'm going to analyze. I'm going to load cases to run. Do not run. So do not run all. And then I'm going to run only the non-linear static. Run, and then run. Non-linear static loads usually take some time to complete the analysis. So we're going to give this a couple of minutes or seconds to finish and push over analysis. view, going to view 3D, then XZ, okay. Plan view, story 2, okay. So let's view 3D, XZ, okay. Go to display, deformed shape. Now display pushover. Make sure you change this one to IO, LS, and CP acceptance points. Okay. Then you can change this to be able to view the life safety and collapse prevention, and how many the hinge point as the form as you continue to change the deformation to the point of collapse prevention. So you can see only two hinge bridge collapse prevention. Most of them are, only a few are able to reach the life safety level. Then can go to display. We will start by displaying hinge results. For load case is push over. I'll go to column label. So this is column hinge. I'm going to go to hinge. Story 4, column 16, that hinge. And then we can check for display hinge results. You can see the current step data, how it changes. And you can go to display, static pushover curve. Now we're going to change the static pushover curve to C SM. So select here FEMA. Now you can see the point where the red and the green curve are joining. That is the maximum displacement. So this is the green and the red. The point they're joining is the maximum displacement. Now if you change this one acceleration to 2.302 and here 0.9556, change here to side class B. You can see the points where the green and the red curves are joining of side class A. If you change to side class E, side class B, set class A. You can print this summary report, then print. Save anything, and then OK. Then you can go to DCM, that is the displacement coefficient curve. So you go to display, you go to static pushover curve, then you change this pushover curve to DCM curve. So you select the plot type to ASCE, then you can just edit, maybe set class B to the period 2.302. Then here should be 0.956. And you can see if I click formatted, you can see the ASCE and FP displacement and base shear. The same thing for the CSM, can be able to see the displacement, SD, SA, and the period in seconds, and it's increasing to a point where it becomes constant. Can remove those. Then you can go to display, force diagram, frame and pan, then select here push over. Okay. So if I click here, display, force, so you can go to file, create report, show report of the project. You can see the lateral, the stories and everything. Then the pushovers, display, combine story spectrum, or just animate. Go to display, right show work diagram for push over, and then OK. So this will be the end of this video. If you like the video, please consider subscribe. See you in the next video.